Section 2.7 covers quantifiers. So we've seen how we can use symbols like and, or, not, and even implies or if and only if to describe mathematical statements. But in this section, we're going to learn two more symbols, or sort of two, and those are the two quantifiers. Right, so we often have these statements of the form for every or there exists. And so we're going to come up with symbols for these. So before you move on, I'd encourage you to pause the video and see if you can think of some mathematical statements that have a for every or there exists in them. They're very common all throughout mathematics. The first of our quantifiers that we're going to talk about is the universal quantifier, and that's the for all quantifier. So we say this usually as for all, but you can also read it as for every. So we're going to think of this guy as either for all or for every. Its symbol is this upside down capital letter A, and to get that symbol in LaTeX, you just need to use that / for all, and that'll work in CampusWire and Overleaf. And what it means is that the following statement, so whatever statement comes after it, must be true for every element in the set. So a for all statement is only true if the statement is true for every statement in the set. So what do I mean by that, right? So usually I'll say something like for all x in S, and then I'll have an open sentence which has the variable x. And so this is true when p of x is true for every single element in S. If it's true for some of them and not true for the other ones, then it's not true. That's for all x in x, p of x. Okay, so what are some examples of that we might have seen? So we could say that for all n in Z, 2n is even. Right, so in English, I could write that as for every integer, 2 times that integer, let's name it n, so we can refer back to it. 2n is an even integer. Right, so for every integer, if you multiply it by 2, then it's even. That's what this statement is saying. We can use this little shorthand that I've written over here to the side. If we just write e sub n, that just means the number n is even. So if I use that shorthand, I can instead say for every n in Z, e sub 2n. So that just means for every n in Z, 2n is even. Did a bad job writing that, so let's fix that up. Beautiful. This isn't very a common notation. We're just going to kind of use it to help us simplify down our statements as we're going through this section here. Alrighty, our other quantifier is the existential quantifier, and that's this backwards letter E, which we can get in tech by using / exists, and this is going to be read as there exists. Or there is a. Okay, so what does it mean? Right, so again, if I have a there exists an x in S such that p of x, there's maybe a little other note here. Whenever I'm actually reading this, I always think of there being an implied such that there. So when I'm reading it out in English, I always pop in a such that because I think that makes it easier to read. And you'll also see that when I write this, I will sometimes put a little st, and that means such that. Because that makes more sense for me of reading it out in English. So there exists an x in S such that p of x. Right. What does that mean? It means that p of x is true, not for every element, but for at least one element in the set S. So as long as it's true for one of them, we can use the existential quantifier that there exists. If it's true for all of them, then we can use the for all. Right, so maybe what would this look like? I could say in English, there exists a natural number less than 7. Right, so in symbols, I would write that as there exists some n in the set of natural numbers such that n is less than 7. So there exists an n and n such that n is less than 7. That's my existential quantifier. The existential quantifier, again, is true as long as there's at least one of them that's true. The universal quantifier, the one we had done before, right, for every n and n, that's only true if it's true for all of them. So that's going to be false because it's not true that every natural number is less than 7, but there is at least one. So then we get that that first statement with the existential quantifier is true. Let's go through and practice translating some of these quantified statements into English. So the first one, if I read it out just using my symbols, I see for all n in z, e sub 6n. So remember, this e sub n is just our shorthand notation right now to mean that n is even. So if I'm going to translate that, my first sort of symbol for symbol translation will give me for all n in z, 6n is even. And if I want to be a little more colloquial with that, I can say every. And maybe I can say every integer, but then I need to be able to refer to that integer later. So maybe I want to say for every integer. Right, we kind of update this as we go. So for every integer. I need to name that integer something so I can refer to 6 times it later. So for every integer n, 6n is even. Or if I wanted to be, less symbol-y, I could also say for every integer, not name it, and just say 6 times that integer. Right, so this is more wordy but less symbol-y, is even. That's what this statement here means. For the next one, again, let's just read it off symbol for symbol. There exists some x in R. I always put in a little implied such that after there exists. Such that it is not the case, not e of x, and not o of x. So there exists some x in R such that x is even, but then we have a not. So x is not even, and x is not odd. So let's see if we can kind of rewrite that a little bit better. Right? There is some real number which is neither even nor odd. So that's another way I could write this. There is some real number that is neither even nor odd. That's what this statement means. Is that true? Sure. Right? Consider 1/2. If I have any non-integer, it doesn't make sense to talk about non-integers being even or odd. So this is in fact a true statement because I found one of them that satisfied that conclusion. Next we have for every n in z, there exists an m in R. Again, we have that implied such that. So even if I didn't write this here, we would still say such that m times n equals 1. So for every n in z, there exists m in R such that m times n is 1. Or I could say maybe we'll do a for each here, for each integer n, there is a real number m such that m times n is 1. And I want you to think about if this is true or false, and we'll talk about that in class. So is it true that for every integer, you can always find a real number to multiply by it that gives you 1? All right, last but not least, we have there exists an n in z. Again, every time I have a this, there exists, when I read it out, I like to have a such that after that. So such that for every m in R, m times n is 0. So there exists an n in z such that for every, or for all, or for each m in R, let's use the symbol there as is standard. Oops, I erased too much. M in R, m times n equals 0. Or there is an integer n such that for every real number m times n will give you 0. So again, I want you to consider whether or not this statement here is true or false. All right, there's a little something for you to do here, so we'll talk about this in class. I want you to consider the statement below. Someone here, so here in this room in this WebEx call, has visited each US state. So I want you to rewrite this statement using quantifiers. So come up with different symbols for each of the statements and rewrite that using quantifiers. And then think about whether or not you think that it's true and how you would efficiently go about determining whether it's true or false, and then we'll see if we can determine if it's true and false during class. There's one more discussion question for you. So I want you to rewrite each of these statements in words, like we did in the previous example, and determine whether or not it's true. So rewrite those all in words, and then determine their truth value. Last but not least, I want to show you how to actually prove these sorts of statements. So we're going to go ahead in class and prove this. So you don't need to think about that on your own if you don't want to, but maybe you can spend a little bit of time, think about how you would go about proving it, or what would need to be done to prove it, and then we'll see what a proof of that looks like in class.